Hi everyone. In Unit 12 of AP Physics C, we're going to be looking at magnetism and electromagnetism. So we'll be looking at magnetic fields and how magnetism is experienced through a force on moving charges and current carrying pieces of wire, so little pieces of wire that have moving charge in them. We're also going to look at how those same two things, a moving charge and a piece of wire with current moving through it, can create B fields that surround them. There's a couple of laws that we can use, just like Coulomb and Gauss were a couple of laws we can use for electric fields. Biot-Savart and Ampere are a couple of laws we can use for calculating the the magnetic field due to those two different types of sources. So let's get right to it. In 12.1, we're just going to get a quick exposure to the magnetic field and the concept of it. Not a lot here in terms of an emphasis on the AP exam, but some important notes here are there are no such things as magnetic monopoles. We cannot isolate a north pole. For every north pole, there has to be a south pole, so we can't just look at a north pole alone. For that reason, the north pole that has magnetic field lines coming out of it must eventually circle around and come back in to the south pole and then go through the magnet like this. So we always have loops that are formed when we map the magnetic field, which is a little bit of a difference in electric field where we could isolate a positive charge or a negative charge as a pole for the source of electric field. So for the sake of multiple choice questions especially, if you're given a magnet, we should know that the magnetic field points away from a north pole. A lot of times we just model this as being directly away from the north pole instead of these little side edge effects, and directly toward the south pole. Magnetic dipoles, again, are not a big emphasis. As in the rewrite, they kind of got added in slightly, but they have not been historically a big focus of AP Physics C. But they're trying to show where this idea of a moving charge creates a magnetic field. And so even down fundamentally to the atoms, the electron spin gives little tiny B fields that if they work together in a material and all align in the same direction, we can create a magnet. That material would be described as magnetic. If they're all in different random directions, then there is essentially no coherent magnetic field, and that would not be considered a magnetic material. So the degree to which these dipole moments can align is mu, which is a permeability. Most common one we'll deal with the majority of the time is the permeability of free space. It is mu naught, kind of like epsilon naught when we had permittivity of free space for electric fields in our Gauss equation. Mu naught is going to be used in Ampere's law equation and has a given constant that's on your equation sheet. The two types of materials you may see on there, but again, this is not historically a focus of AP, is paramagnetic and ferromagnetic materials. And so really this is just the degree to which they can amplify a magnetic field that's external around them. So slightly magnetic would be things like aluminum, gold, and copper. They're not going to be magnets in and of themselves, but they can slightly, what would be in electric fields, polarize, but in magnetic fields it's just aligning those magnetic dipole moments when there's an external field applied to them. Ferromagnetic fields are easily magnetized, and they will actually hold on to that. Although not forever, they will hold on to that magnetic field once they are placed in an external magnetic field. You may see this if you wrap a wire around a nail, for example. That nail will help to amplify the external field, and iron can carry a magnetic field by itself without having that external field still there. 12.2 is where we're really going to get into the meat of AP Physics C in the exam. So we are going to be using the rest of this Unit 12 quite a bit. So the first thing is going to be magnetic force on moving charges, and then the next thing we would do is the magnetic force on the moving charges within a wire that we would define as current, so the magnetic force on current. And so we're going to be introducing a right-hand rule, which is the first right-hand rule that we're going to use is going to be through the concept of forces, and that's this kind of a right-hand rule. The curl one that you may have noticed where it goes like this is going to be used for Biot-Savart and Ampere later on, and you can check that out here in 12.3 and 12.4. The magnetic force here is given as a magnitude of QV times B. This cross product and the vectors here are just to show you the right-hand rule. So you can see in the diagram I have here that we're going to have in our gesture, velocity is going to be along my finger here. So you point in the direction it's going. I was saying that then we can have a mnemonic device, as you can see here, where the first variable in our cross product is going to be the index finger, or if you want to remember, it's your arm, because it points along your arm and index finger. So you point your forearm in the direction that the object is moving. This has a mnemonic device with torque, where R cross F, you could think of R as being your arm, right? Your forearm along here, and finger. So it goes like this, right? And then your fingers, in this case, your three fingers that you have right here. So these three fingers right here are going to point in the direction of force F. F stands for fingers. So for our equation here, that would be the magnetic field is your fingers. And your thumb's going to point in the direction of the torque. I'm sorry, the force, magnetic force. In our torque expression, you can see the tau here, the Greek letter T, would be useful for thumb. So we use the torque equation as a mnemonic device here that we can apply to any cross product to see like which variable goes with which part of our right hand rule gesture. Instead of a moving charge that's just moving through space, we often have moving charges that make up a current that's in a piece of wire. So we showed where this moving charge equation can be derived into the current in a wire, but it's still the same cross product, and you can think of it exactly the same thing. We have, of course, the direction the charges are moving, and that would be the way the current is. Current gets its direction from the length vector. So IL is typically bundled together as being a current carrying piece of length in a wire. B is again going to be the fingers right here. And then you have your thumb, that is the direction of the force. Again, applying our mnemonic device of torque, this first vector is your index finger or your forearm. Second one are your three fingers, and then the thumb is the force. So whenever we're calculating the force experienced by a moving charge or moving current through a length of wire, we are always going to be doing the force equation that involves the direction defined by the right-hand rule. In 12.3, we're going to be looking at how these same moving charges and pieces of current through a wire create the magnetic field instead of experience it. It's kind of like a charge can create the electric field and be a source charge, or we can treat that point charge as being a victim and experiencing a force due to someone else's electric field. It's the exact same thing here. So in 12.3, we're going to be switching gears and looking at how this moving charge can create B fields. So we're going to first look at the current carrying wires. And in this case, it's going to be the right-hand rule that is modified here. We call this a curl. And so this curling method like this or like this is what we use for creating the B field around a current. So the idea is with your thumb, you grab the wire, figuratively speaking. You can see that in the graphic as well. So in that graphic, you can see I'm grabbing the wire, and then it's going to curl around that wire in the counterclockwise direction. You can see that if I were to look at this from above, there would be a current coming out of the page, and it would go counterclockwise. These loops that are counterclockwise represent the magnetic field loop around that wire. A little bit of visualizing here that can be tricky. So if we look at this from a side view, the circle would be flat, and we can look at the edges as coming out of the page and into the page. Mathematically, we have one of two ways that we can solve for the B field that's created by these currents. And the first way is going to be exactly the same thing we did for Coulomb's law when we had those linear charge distributions. So we had like a thin ring, which is like a current loop for us. So we have like a ring, and we had to look at it along the central axis. We could have a semicircular arc or just a partial circle, like an arc, where we're looking at a point at the radial center of it. Or we can have a finite, meaning a line segment of current, and we'd be looking at a perpendicular bisector. The word finite is very important there. And of note, the perpendicular bisector problems are not going to be solvable with calculus, but you can still set them up and not solve, as we'll look at in a few examples here. Both Biot-Savart and Ampere's law both use the curl method to try and determine the direction. This whole little concept map here and explaining this is going to be kind of complicated. In a simplified view down here that I'll show you is, if we get rid of the cross product, since we already know the curl is how we're going to get this, and we then integrate this whole thing, we have mu naught, which is that permeability of free space, 4 pi. IDL is an important thing to recognize. Those are kind of bundled together since it's current through a tiny piece of length, and that tiny piece of length L is the vector that defines the way the current's moving. And so we want to keep those in mind, because IDL is the source of the B field. So it's a little tiny piece of wire that has current going through I. So IDL, the current carrying piece of tiny length, is what creates this looping B field drawn here in blue. So at the very top of the page, that current is going into the page, this way, into the page, which is going to create the clockwise loop. And at the very bottom of the loop, it's coming out of the page and should be creating then what you can see is that counterclockwise loop. At that center of the loop, the thin ring, those B fields are going to be parallel to each other and therefore add. As we look at what's constant and what's changing for different IDLs, we realize that they're all the same distance r away. They all have the same current, and mu naught over 4 pi are constants, right? So that means that the integral of dl is simply going to be the total length, and that total length is going to be the circumference. And so this actually reduces to algebra, and almost every time the Biot-Savart problems are going to reduce to algebra. So this should happen very, very often. This is a good one to memorize potentially. It's easy to derive though, but we can use this pretty often in different problems we see in multiple choice, or you can choose to derive it if you like. Second example would be when we have the loop, but we're along the central axis some distance x away. So I want to first, just like with Coulomb problems, I want to make sure that I'm figuring out what kind of cosine and sine theta we have here if we have angles involved. And so I'm going to be looking then at, let's look at the bottom one first. The bottom IDL, meaning current going through a little tiny piece of length, would be coming out of the page. And so it's going to create a looping B field that's like this, right? And in that case, then you can see if your radius is this R, the B field is going to be looping counterclockwise, right? So it's going counterclockwise around, and it's always going to be a B field perpendicular to the radius, right? Perpendicular to the radius. That should make sense, because if we have a current here and we look at any point on this loop, the B field is always pointing tangent, right? It's literally tangent looping around that B field. So any R value that I make, the B field should be tangent to R. So I know it's going to go up and left instead of down and right because of the curl. As always, in order to figure out if this is cosine theta or sine theta, I need to make a right triangle, and I'm going to use those spatial dimensions, x, capital R, and lowercase r, to define my sine theta and cosine theta, and also to define the r since it's not given. I can see here, due to this one that's going up and to the left, the B field, and due to my top one that's coming into the page, and perpendicular to that would be down and to the left, the vertical components are going to cancel out, and then we have a horizontal component in this case that's pointing toward the center. And so I want to use B cosine theta if I'm using this angle right here. It is a little confusing, but if this is the angle theta, then 90 degrees would make this angle down here its complementary angle, which means that this angle here would have to be theta for the theta that we have drawn. Regardless, if you did this right, you could also use the top angle and do sine theta, but either way you get capital R over root x squared plus capital R squared. And obviously you can find the R value by doing the Pythagorean theorem. So now we're going to get going, but we have cosine theta here, so we have to pull out any constants we have, which we have quite a bit of them. So the R value is going to be the same. It creates almost like a cone shape with a radius R, and that's going to be the same for any IDL that we have, current times DL. Cosine theta is also going to be the same. So again, we're just integrating DL, which is the total length, 2 pi R, and that's going to be using capital R. And we can just substitute that in terms of givens and be all good. With a semicircular wire of current, you can see here that we have IDL. At the center of this curvature, we have a B field that's going to be going into the page. And because we have, right, the current, which if it's going this way, right, if we hold this wire at any point on here, our thumb would point in the direction of the current. Our fingers would then curl into the page here. So it should be something like this. If I'm grabbing right here, something like this. Okay, so then we put all the constants, and we're again left with just the integral of dl, which in this case, the total length is going to be pi r. It's a half circle, and so we have our equation there. In this case, you can see that it's a finite wire, right? So this has a clear beginning and end, and then there's a point P that's along a perpendicular bisector. You can see it's L over 2 and L over 2. And so in this case, then, we can still use the curl to get the direction of the magnetic field, right? Which is going to be the direction like this. So it's going to be coming out of the page. And we can set this up the same way. Let's look at what the R would be. We can try and define that R using the spatial dimensions, x, c, and little r to define R. And then we can also look at the component sine theta as well. And define that in terms of the givens. And the problem is that this is just a kind of a tough integral for us to do by hand. So this says write but do not solve it. So we got to make sure on those that we put the limits in. Those are always going to be emphasized. And the limits here would be, since we're integrating from negative L over 2 all the way to L over 2, those have to be our units. In Ampere's law, we're going to feel a lot like Gauss, but there are some important distinctions to make here. So first thing with Ampere's law we have to recognize is when this is going to be appropriate to use. And just like with Gauss, if you have infinitely long, not finite, but infinitely long wires or cylinders, you can be inside the cylinder or outside the cylinder. The wires are essentially cylindrical in shape, but they have to be infinitely long. They can also be given, instead of charge density, like with Gauss problems, insulators, right? We could also be given current density. Conductive slabs, which would be like a tabletop where there's a thickness to it, and it would have to be infinite in size. It had to be like very, very big. Also a plane would fit into this as well, just like with Gauss, and those would be carrying current through them. The one that's different here is we're not going to be doing spheres, but instead we do solenoids, which are coils of wire, and that would be using Ampere's law to derive it. So we'll look at all those examples here in a moment. We're still going to use the curl, right, to get the B field that's around those current carrying charges, conductors. So with this then, Ampere's law is essentially breaking down the idea that if we have some kind of a looping B field over some length, this closed integral says that that line has to close off around into a loop. So it can be a circular loop, a rectangular loop, etc. But it has to loop. It's not going to have a beginning and ending point like a finite line. It's going to be, you have to close those ends off and make a loop. And that B field is going to be along that loop. So the loop that we use in this integral, or define with this integral, is going to be the B field's loop. So the B field acts parallel to some dl that makes up an overall loop. And that's going to depend on how much charge goes inside of it or passes through it, right? Because it circles, the B field circles the current. So how much current we have within that loop is what's going to define how much magnetic field B we have. So we have mu naught, a constant, the permeability of free space, times how much I we have passing through the area of our B field loop. Just like with Gauss, we have a left side and a right side to do here. So we're not going to integrate this expression. We're going to use high degrees of symmetry, meaning we're going to make sure that we define our magnetic field along a loop where the B field is uniformly distributed along the lines. It's going to be the same at all dl's. So that means B is constant for all dl's, and then we can bring out the constant B field and do the integral of dl. And that means that we can just decide how long is our loop that has the B field that we're solving for acting along it. The right side can be a little bit trickier because we can have an easy situation where we know the total charge is passing through, or we can have a fraction of the total charge where it's a proportion, just like in Gauss, where we knew that it was some fraction of the total charge. We can also be given the current density as a function, and we can integrate that to get the I enclosed. So look at some examples there. This would be an example where we're enclosing the total current I, and so that would be a pretty easy one because I enclosed is just I, and the B field that's looping around it would be the same at everywhere on this loop, this circle of distance 2 pi r. And there you go. And this is a good one to memorize because it happens all the time on the AP exam and something we want to have quick access to. If we look at this wire, but what's the magnetic field inside the wire, where we have little r smaller than the radius of the cylinder, then we again have the B field is going to be uniformly spread out along this whole thing as a constant, and then the whole loop is 2 pi r. But this pink shaded area is the area through which the current is passing that creates that looping B field. Right? So the B field only depends on the amount of current that's passing through its loop. So I have to define that. It's not the total current I because there's some that's outside of our loop that doesn't affect it. So I had to set I enclosed over the spatial dimension that I enclosed resides over. In this case, it's through the area defined by our smaller looping B field with radius r. So it's a circular area of pi r squared. And I'm going to set that equal to, because they give me the total current and the total radius, I'm going to set that equal to the total current over the total cylindrical radius or cross-sectional area here that we have pi big R squared. That's the total area through which the current passes. And then I can solve for I enclosed similarly to how we did insulators with Gauss. This is a very common example. We're going to be looking at the force on one current, I1, due to a different current, I2. So in this case, I1 is the victim experiencing a force, which is going to be a right-hand rule problem. And then I2 is the source of that B field, which is going to then be an Ampere problem, which is a claw. So you can see the red part is Ampere, which is what we're doing right now. And the blue part over here is the force on the current carrying wire I1, and that's going to be from 12.2. In terms of solenoids, we will have then a solenoid or a coil of wire, and each of these individual little loops of current, right, that maybe it's coming into the page at the bottom and out of the page at the top, each have their own field at the middle, right, which I'm modeling down here with these red arrows for the B field. And then outside of it, although they do loop around, they're very diluted, especially when compared to how they're overlapping on the inside. So we really only care about the B field inside. And this creates a uniform magnetic field inside these coils. So kind of like parallel plates create a uniform electric field in the space between the plates, like, right, then the solenoid will create a uniform magnetic field that's controlled by the current inside the solenoid. So when we make our B field loop, then we're going to make a rectangular loop so that the top of it's going right through the middle where that B field is. And then it's 0 essentially here on either side, and it's essentially 0 on the outside. So the B field is only acting parallel to the top because it's 0 on the other three sides. So our total length where the B field is constant is L. So user-defined variable in most cases, but in this case, L was actually given as the length of the solenoid. So it's okay to have this in our final answer. Mu naught then is going to be defined as a constant, and the I enclosed is going to be defined as n times I, where n is the total number of loops we have, kind of acting as like an amplifier. Each loop contributes a magnetic field because each one of these is creating a loop around it with the B field. So it's like a magnifying effect. And we could, instead of be given n and L, we could also be given the turn density, which is lowercase n, and that's defined as how many turns we have per meter. And that's another way that we could write this. For a slab problem, we'd have a current moving parallel to the slab, and we could have a magnetic field that's inside it, for example. And the B field is actually only going to be acting along the top, well, in this case, the bottom as well. The sides would have 0 because we have current that's the equal amount of current to the right and an equal amount of current to the left if this is truly infinite. So there would be zero field on the sides, but you have just enough extra charge below it when you're up here to create a B field that's moving to the left, and then below it you have more current above it, so that means you're going to have a B field going to the right, totaling a distance of 2L, and then we can define the I enclosed as residing over the area defined by the length times width, and we can get the magnetic field that way. Should be noted that if we are going to try and derive an expression for a B field and we're given a current density, we can write that whole integral out, integrating the current density with respect to area. So we have our J naught R squared, and dA we have to use as a circle of circumference 2 pi r with thickness dr. We're creating like a little ring with a thickness dr, and then we're integrating those angular rings as you move out with the radius. So that then creates our expression. And if they had said that it was, instead of inside, if it had been outside, so if our radius r, little r, was bigger than this whole thing, then that only really affects the limits, because we had the current defined only until A, not all the way outside if our radius r is larger, right? If we're inside of it, then it's going to be confined to little r as it's pictured here. I hope this was of help, and please see me with questions. Thanks.